Functions, exponential graphs. So an exponential function is the one that takes the form a times b to the power of x, where a is a coefficient, b is a constant, and x is a variable power. If we have b as the base number and b is a whole number, so a whole positive number, then what we get is an exponential growth curve. So bacterial reproduction would be an exponential growth curve. If b is less than 1, then we get a graph that is sloping down. So in other words, if we get a fraction, so we would say, i.e. if b is between 0 and 1, so a fraction, then we get an exponential decay curve. So radioactive decay would be an exponential decay curve. So when x is equal to 0, then what we end up with is 1. So in other words, anything to the power of 0 is always going to be 1. So what that means is that when x is 0, the graph is going to cut the y-axis, and it'll always cut the y-axis at the coefficient a. So if there's no coefficient in front of the function, so say for instance here we have f of x is equal to a half to the power of x, we have f of x is equal to 2 to the power of x, and we have f of x is 8 to the power of x. So these three graphs, the red, the blue and the green, all of them in this case, the coefficient in front of each of those is 1. So what that means is each of those graphs cut the y-axis at 1. Every single one of them. But if we were to multiply each of those graphs by a number, then the graph would end up shifting its position. So this is like our transformation. Okay, so let's look at how can we draw our graphs. So if we're looking at page 150, we're going to do question 1 as our first example. So we're going to graph y equals 2 to the power of x in the domain of minus 2 less than or equal to x less than or equal to 3. So we start by making out our table. So we have 2 to the power of minus 2, 2 to the power of minus 1, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and 2 to the power of 3. So 2 to the power of minus 2 is a quarter. So we'd be out to minus 2 and up to a quarter. 2 to the power of minus 1 is a half. So we'd be out to minus 1 and up to a half. And you can, of course, write that as 0.25 and 0.5. 2 to the power of 0 is 1, so it's out to 0 up to 1, as we were explaining in the last slide, that we would be looking at anything to the power of 0 is always going to be 1. So the graph will cut the y-axis at 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And 2 to the power of 3 is 8. So if we sketch our graph, our highest y value is going to be 8, our lowest y value is going to be a quarter, and our x-axis then will be ranging from minus 2 to 3. So if we sketch our graph, we can see that is an exponential growth curve. So it's increasing, and we can see that it cuts the y-axis at 1, 0. And what's interesting to note here is that the graph will approach y but never cross it. So even if we were to keep continually plotting it, it would never ever cross the x-axis. It would only ever approach it. And that's because there is no value that would give no power of 2 that would ever give a negative value for y. So the second example we'll look at is question 5, which is 5 to the power of minus x. So if we sub in our values again, we're going to have 5 to the power of minus 2, 5 to the power of minus 1, so making sure you're using brackets there, so it's minus x. So what that gives us for y then is 5 to the power of 2. So minus 2 is plus 2, so 5 squared is 25. We're going to have 5 to the power of minus 1, in other words 5 to the power of 1, which is 5. 5 to the power of 0 is 1, so anything to the power of 0 is 1. 5 to the power of minus 1 is 1 over 5. 5 to the power of minus 2 is 1 over 5 squared, so that's 1 over 25. And 5 to the power of minus 3 is 1 over 5 cubed, so that's 5 cubed is 125. So of course, for these last three, you're better off writing them in decimal form for graphing. Okay, so what does that look like? So what we actually see here, and it's important to note, is that that's y equals 5 to the minus x. So minus means 1 over 5 to the power of x, which is the same as saying 1 over 5 to the power of x. So this time we actually see this is a fraction. So in other words, the number is between 0 and 1, and therefore we can see from our graph that it is an exponential decay. So unlike the previous one was an exponential growth, this one is an exponential decay curve, and that's because it's a fraction raised to a power. The second thing to note is that it cuts the y-axis at 0, 1 again. And that's because we have anything to the power of 0 is 1, and the coefficient there of 1/5 to the power of x is 1. And the same again, it always approaches the x-axis but never crosses the x-axis. So even though it looks like it's sitting on the x-axis, because 1 over 25 is an extremely small number, if I zoomed in and zoomed in and zoomed in on that on GeoGebra, we would find it would never actually cross it. It doesn't even touch it. Now, just for the purpose of your graphs when you're sketching them, always have it sitting just slightly above it. So never touches the x-axis. Okay, so one last graph to sketch, and we're going to do question 6. So this time we do have a coefficient in front of our exponential. Okay, so we have 3.5 times 3 to the power of x, whereas in the previous one here, the coefficient was 1, and also the coefficient was 1. So if we have 3.5 multiplied by 3 to the power of minus 2, 3.5 times 3 to the power of minus 1, 3.5 times 3 to the power of 0, and so on. So that gives us an output value for y. So if we fill out our table for our y values, again, we're going to get fractions all the way down here, so we may as well write our answer in decimal form for the purpose of sketching. And again, we see we have an exponential growth curve. So just label this function, so that's y is equal to 3.5 times 3 to the power of x. So I was making sure we label it. And we say note. So again, exponential growth. And that's because it was 3 to the power of x. So a whole number raised to the power of x is going to exponentially grow, as opposed to the previous one, it was a fraction raised to a power, which is going to exponentially decay. This time, however, we see that it crosses the y-axis at 3.5, and that's the coefficient in front of the 3 to the power of x. And again, it never cuts the y-axis, or x-axis, sorry. So it only infinitely approaches and gets closer and closer and closer, but never actually cuts it. Okay, so the graphs that you're going to draw for me now are going to be 2, 4, and 7. And then we're going to look at how do we read a graph. So this is going to be type 2. So in this case, we'll be working backwards, where we're given the graph and we're asked to identify what is this function. So in other words, what is A and what is B. So we have to note that A is always going to be where it cuts the y-axis. So we say to find A, so in other words, A is the y-intercept. So in this case, we can see the y-intercept is 3. So then we have to find b. So to find b, what we do is we choose a point from the graph. And sub it into y equals a b to the x. And solve. So if I pick a point 1, 6 on my graph here, so I go out to 1, I go up and I go across, I see that my x value is 1 and my y value is 6. Then that means if I sub it into y equals a times b to the x, well, y is 6, a we have solved to be 3, b we're looking for, and x is 1. So if I divide both sides across by 3 there, I get 6 divided by 3 equals b to the power of 1, which is just b. In other words, then I can say, well, b must be equal to 2. So now I know what a is and I know what b is. I can therefore say that the function here, this purple line, is represented by the function y equals a times b to the power of x. So in other words, the function is y equals 3 times 2 to the power of x. So you're going to do question 9 and 10 on page 150.